This lab will focus on magnetic fields and forces. We'll first look qualitatively at fields by mapping the field lines with the dipole. We'll then look quantitatively at the Lorentz force, the force due to a magnetic field on a moving charge. We'll map magnetic fields by using the fact that a field exerts a torque on a magnetic dipole. Our dipole in this case will be a compass needle. We have two permanent magnets at fixed locations. Red is the north side of the magnet and blue is south. You'll slide a compass around through the fields and record the direction in which the field points. Check every once in a while that your compass hasn't had its dipole reversed by making sure it still points north toward Lake Mendota. Then rotate one of the magnets so that the two magnets now point in opposite directions. Then redo your measurements with the compass. You can also observe the field directions at many points at once with an array of dipoles. After you've sketched the field lines, you'll get a feel for the shape and uniformity of these fields by replacing the compass with a small bar magnet you'll hold between your fingers. Move the bar magnet around through the fields and try to note both the torques you feel on the magnet and the net force. You'll do this for both the magnet configurations. You can then use this information to decide which of the two configurations would allow you to produce the most uniform B field. In the second section of the lab, you'll measure the force on a moving charged particle due to a magnetic field. To do this, you'll need to create a uniform magnetic field whose magnitude you can calculate. In the previous section of the lab, you saw how to create uniform fields with two large dipoles. That's what you'll do again now, except instead of permanent magnets, your dipoles will be large rings of current. You'll need to connect a current source to your coils. Connect the positive lead to one of the coil inputs and the ground lead to the other, and turn up the current to 2 amps. Current is then flowing from the positive lead through both coils and back into the ground lead, and you'll now have a magnetic field at the center of the two rings. Now that you've got a uniform magnetic field, you'll need a source of electrons at a velocity that you can calculate. To do that, we'll use a heated filament as the source of free electrons, and then we accelerate those electrons with a known electric potential. You'll connect the outputs labeled filament from the current source to the top and bottom connections of this plastic block. You'll also connect the output labeled anode to the side connector on the plastic block. This output provides the voltage that will accelerate the electrons. You can then turn up the heating current to the filament. Do this slowly to avoid breaking the filament. When the current gets to about 12 milliamps, you should have a visible beam of electrons inside the glass globe. Here you can see the beam of electrons curved due to the magnetic field of the coils. You can change the current to the coils and see the radius of the beam change. You'll use these markers inside the globe to measure the beam radius. You can also change the accelerating voltage of the electrons to change their initial velocity. This will also change the radius of the electron's motion.